Good afternoon, students, and welcome to distance learning from the kitchen of Spence Towers. Now, I hope you're getting used to this idea of distance learning and that you're getting some value from it. As far as double award science is concerned, you might remember that when we were back in school a couple of weeks ago, we were in the middle of Unit Physics 2, and we just completed topic 3, which was current electricity. Now, last week I sent you out the topic test for this topic, and some of you did it and returned your solutions to me. What I'm going to do now is attempt to look at topic 4, which is electricity at home. Now, for this you're going to need your white notes, which is this booklet here. There it is. Okay. And we're going to be starting at page 70 in a little while. Okay. Now, this is page 70 in the white notes, and I've written out here some learning intentions. So, in this video and in this lesson, we are learning, why do metal wires have resistance, and why does a wire heat up? How can we calculate the amount of electrical power delivered by an electric current and the amount of energy that it's transferred? Okay, so in this lesson, we're going to, by the end of it, we should have been able to do these things. We should be able to explain why metal wires have resistance, why they heat up in terms of electron-atom collisions. We should have defined voltage more precisely than we have done previously. You should be able to recall the formula for power. You should be able to derive and use the formula for electrical power, and then you'll be able to practice those formulas, practice the use of those formulas on a question sheet. And the reference for this lesson is the white notes, page 70. Okay. Now, so what that's actually going to mean is that we're going to look at how electricity is used to power our devices at home. So domestic appliances like computers, televisions, kitchen appliances like your washing machine or your kettle, and so on. In the course of this lesson, we'll go on a little field trip to visit a domestic appliance. And at the end, I'll give you a little exercise to do. Okay, let's get on then. So, what we're going to do here is I'm going to talk for a bit as if we were just in class about why metal wires heat up. We'll make some definitions. We'll go and look at a demonstration of this, and then we'll do some formula practice. Okay. Now, to link in to what we were looking at before in topic 3, we can remember what happens when an electric current passes through a conductor, such as a piece of wire. So if you've got a metal conductor, which could be a piece of wire, we know that you can make an electric current flow through it. An electric current is just a flow of electrons, and each electron carries a small amount of electric charge. The symbol for electric current is big I. Remember, intensité du courant, the intensity of the current. Now, a current will not flow by itself. It needs a battery or some sort of source of electromotive force to push it along. And we can supply that by connecting a battery between the ends of the conductor. And the diagram for that would look something like this. Now, the push that the battery supplies, we call that the voltage, big V. And we said that voltage is basically the push of energy that the battery gives to the electric charge, to the electrons, to make them flow through the conductor. Oh yes, I forgot to say that this video ought to last about 30 minutes all in. So that's all you have to be here for. Now, we did this experiment. We applied different voltages to a metallic conductor. Ours, I think, was a piece of constant tan wire, and we measured the current that flowed through it. And when we plotted the results on a graph, we plotted the voltage applied on the y-axis and the current that flows on the x-axis, and it looked something like this. It was a straight line passing through the origin. Now, that told us that as the voltage that we apply increases, so the current that flows through the wire also increases. But furthermore, as the voltage increases, the current increases in proportion to the voltage applied. So the current is directly proportional to the voltage. And that result is known as Ohm's law. And it's important because all metallic conductors obey this, provided that their temperature remains constant. In other words, the temperature of the wire doesn't change. Okay, now, all right, so all metallic conductors do this. They all will conduct a current when a voltage is applied, but some do it better than others. So current flows more easily through some conductors than others. So if we get, for example, a conductor like a piece of copper wire, and we apply a voltage to that, then the current that flows through it is quite large. So current flows easily through a piece of copper wire. But if we got a wire made of a different metal, say nickel chrome, then what we find is that this will also conduct a current, but it won't be such a big current as the copper will conduct. So current does not flow through so easily through nickel chrome. And therefore we say that the nickel chrome has more resistance to the flow of current than the copper does. And we define resistance as the ratio of the voltage applied to the current passing through the conductor. Okay, R equals V over I. Now, remember, just while we're at it, that current is measured in units of amps, symbolized A. Voltage is measured in unit of volts, symbolized big V. And resistance is measured in unit of ohms, represented by the symbol omega. All right, so far so good. Now, why should it be that nickel chrome has a greater resistance than copper? Why does it let through less current? Well, we can explain that by thinking about, because of what we know about the structure of metals. So if we took a little piece of copper wire and we could zoom in on it and look inside it, so we could see a short section of it, and it looked something like that. Well, copper wire is made of copper atoms, and the atomic number of copper, its Z number, is 29, which means that each copper atom has 29 protons, but it also has 29 electrons orbiting around it. Now, the copper atoms are arranged within the metal in a regular pattern. Copper is actually a crystal. It has a crystalline structure where the atoms are arranged in a regular order, a little bit like this. And we call that the crystal lattice. Now, each one of those atoms has got 29 electrons orbiting it, and they're arranged in the electron shells according to the rules for filling up the electron shells: 2 in the first shell, 8 in the next one, 18 in the next one, and that makes 28. So the 29th electron is all by itself in an outer shell. Now the first 28 electrons, because they occupy full shells, are strongly bound to their atoms. But the 29th electron, because it's on its own in the outer shell, is not bound so strongly. Therefore, with just a little bit of energy, it can escape and break free from its atom and become a free electron. And that means that each atom can liberate one electron, one free electron, which can go off and move around at random, like a tramp, wandering around through the crystal lattice. Now, since each copper atom has lost one electron, it has technically become a copper ion. So each of these atoms is actually a copper ion. It's a Cu+. Now the copper ions can't go wandering because they're fixed in the crystal lattice, but the electrons can. Now, wandering electrons don't constitute a current, but we can make a current flow because if we apply a battery to the conductor, like this, then that creates an electromotive force inside the copper. The negative terminal of the battery tends to repel the free electrons and push them away. The positive terminal of the battery makes one end of the wire positive, and that tends to attract the electrons. So the electrons begin to drift slowly through the lattice, like so. And that drift is what constitutes the electric current. So, an electric current is a flow of free electrons through the metal. So, we have a current of free electrons. Now, the electrons don't get a free passage through the metal. An electron is drifting along, and then it will tend, sooner or later, to bump into one of the fixed copper ions. And when it does so, that will basically slow it down or stop it moving altogether, or even bounce it back the way it came. It's a little bit like a bumper car trying to make its way through. Well, instead of having a clear bumper track rink to go round and round, it's got lots of obstacles, and it gets accelerated along, but when it hits one of the obstacles, that slows it down again. So we have millions and millions and millions of free electrons in the metal, but as they make their way through, as they drift through, so they bump into the fixed copper ions, and that slows their progress. So therefore, the flow of electrons through the metal is limited. That means that the overall current is limited. And that is what causes the metal to resist the flow of electrons. So that's where resistance comes from. Resistance is due to the collision of free electrons in the metal with the fixed atoms or ions of the metal. So we have electron atom or electron ion collisions, and that's what limits the flow of current, and therefore that's what gives the metal its resistance. If there were no collisions, then the current could flow without limit and there would be no resistance. Okay, that's not all. Something else happens as well. When an electron is pulled along, it accelerates. If it accelerates, that means it's gaining kinetic energy. But when it collides with a positive ion, it loses some or all of that kinetic energy. Now, the energy can't disappear, it has to go somewhere, and where it goes is it becomes kinetic energy of the fixed positive ion. And the ions can't move around, but they can vibrate in position. And so they vibrate more vigorously with more kinetic energy. And if all the ions in the metal vibrate more vigorously, then we see that on the macroscopic scale, on the large scale, as the metal getting hot. So because of these electron atom collisions, which give rise to resistance, the metal as a whole gets hot. So we also see a heating effect. And that's why a metal tends to get hot as a current tends to pass through it, because of the collisions of the electrons with the atoms inside the metal. Okay, can we see that in action? Yes, we can. To do that, we have to go on a small field trip here in the kitchen, although actually, for technical reasons, the field trip is going to come to us. So, excuse me a moment. Right. Now, this is my kettle. There it is. It's upside down, of course. And if we position the camera so that we can see inside it, like so, that ought to work. Well, it doesn't look like much, but I'm going to plug it in over here and then switch it on. Okay, now I'm not going to put any toast in it because the toast would get in the way and we want to see what happens. Now, can you see that? Can you see that the heating element inside, all those little wires running across like this, are getting red hot? So, what's happening here is that the current from the mains is flowing through each of these little wires. Millions and millions and millions of free electrons are hammering through the lattice of metal atom ions, and they're colliding with them. And each time an electron collides with an ion, it gives it a little bit of energy. And millions of those collisions result in the wire as a whole getting red hot. Now, I'm going to hit that because I don't want to fry my camera. That's quite hot. Okay, and that's what's going on. So I'll take that away. Okay, toast crumbs. Now, let's consolidate a little bit. If you grab your white notes, your Physics Unit P2 booklet, and if you go to page 70, and find page 70. There's page 70. Now, while you're doing that, I'll just let the cat in. Come in. Yes. Okay. Now, I'm not actually going to write on this page because if I mess it up, I've only got one booklet. So I've printed the page, and this is what it looks like. Now, the first thing, we don't even need to write anything here because it's written for us, but we might want to highlight. So, electricity in the home. And in the booklet, this is annotated as topic 4. So it's electricity at home. Now, we know that an electric current generates heat when it passes through a metal wire. Why does this happen? Well, it's because of this idea that as the electrons pass through the conductor, they collide with the fixed atoms or ions in the metal. And that's pretty much it. That's really what the key idea that we want to take away from this. Okay. So electrons pass through the conductor, they collide with the fixed atoms. Now, as we saw, in these collisions, the atoms lose kinetic energy. That's actually wrong. That should be electrons. So the electrons lose their kinetic energy, atoms gain kinetic energy. This causes the atoms to vibrate faster, and faster vibrations mean the metal as a whole has heated up, it has a higher temperature. So we could call this the heating effect of an electric current, which is also known as Joule heating, because, I don't know why actually, but I suppose because the electric current heats up the wire and it gets joules of energy. Now, hairdryers, toasters are both using the Joule heating effect of an electric current. So, that's that. Okay, how are we doing? Let's have a look at our success criteria. So we've tried to explain why it is that metal wires have resistance, see you later, and why they heat up in terms of electron-atom collisions. Okay, so we've seen that metal wires resist the flow of current because of the collisions between electrons and atoms, and this also causes them to heat up. Right, the next thing is to define what we mean by voltage. Okay, so we can say, a little bit, what is voltage? Okay, well, we said earlier that voltage is the push of energy that makes the electric current flow. Now that's not a great definition, because a push is a force and energy is energy. So a push of energy doesn't make a lot of sense. We do have a unit of voltage, which is the volt. Now, the way this is set up, how can we do this? How is it defined? We can define voltage better by just developing this a little bit. We could say that voltage is a push of energy. Well, we can define it as the energy per unit charge. So, voltage is the amount of energy that each unit of charge gets as it goes through. The energy that it's given by the battery. Now, voltage is measured in volts, and so what is a volt? Well, 1 volt means that 1 joule of electrical energy is, well, transferred, given or received by 1. Now, can you remember what the unit of charge is? It's the coulomb. Okay, let's just recap this, because this is a little bit tricky. Right, so voltage is the push of energy. More specifically, it's the amount of energy given to each charge. Now, we think of the charges that are moving in the current as the electrons. But an electron carries a very tiny amount of charge. So we measure the charge, instead of considering just one electron, we think of lots and lots of electrons all together. And we measure the charge that's carried by the electrons in units of coulombs. 1 coulomb of charge would be the total charge carried by many millions of electrons. So we can think of the current as being a flow of electric charge going through the conductor, made up of many millions of electrons, but we measure that charge in coulombs. Remember that if electric current is a little bit like a flow of water, The flow of water is made up of many millions of water molecules, but we don't count the water molecules, we measure the amount of water by the volume in litres. Well, likewise, we measure the charge in an electric current, not in terms of the individual electrons, but in terms of the total amount of charge, which is measured in coulombs. Okay, so then we measure the voltage as the amount of energy per electron or per unit charge, and that means that it's the energy per coulomb of charge. And 1 volt of voltage is 1 joule of energy per 1 coulomb of electric charge. Okay, so the formula for voltage then would go something like this. We would say that voltage is equal to the amount of energy that is transferred divided by the amount or the quantity of charge that has flowed. Now, if we symbolize that equation, V for voltage, E for energy, and Q for the quantity or the amount of charge measured in coulombs. Okay, now if that seems a bit tricky, don't worry, that's a little bit beyond our spec actually, but this formula is going to come in useful in a moment. Now, yes, okay, yes. Now, if the voltage is the energy divided by the charge, we could rearrange that formula and we could say that the amount of energy that is delivered by a current is equal to the voltage, that's the energy per unit charge, multiplied by Q, the quantity of electric charge, that's the number of coulombs. And that might be useful. Okay, let's carry on. We're at 27 minutes and I said this was going to be 30 minutes, so we're going to run over a little bit. Okay, electrical power. Well, you might remember the general formula for the power of a machine, and a machine can be anything. It can be a toaster, it can be a cat, it can be me, it can be a Ferrari. Any machine, anything that transfers energy. And the difference between power and energy is that power is the rate at which energy is transferred. So it's how much energy is transferred per unit time. So power is the work done or energy transferred divided by the time taken for that energy to be transferred. And in symbols, P for power is equal to W or E for energy transferred over T for time. P equals E over T. Now, if we rearrange that formula, that would tell us that the amount of energy that's transferred by a machine is equal to the power, which is the amount of energy per second, times the time, which is the number of seconds which that machine works. Okay, now that is completely general. That's the power of any machine at all. But what about if the machine is one which is transferring electrical energy? Now, a machine that transfers electrical energy is any kind of component. It can be a light bulb, it can be a motor, an LED, anything. Okay, so, well, we want to say that P for power is equal to energy divided by time. And if we go back to our definition of voltage, voltage is energy divided by charge. So energy is equal to voltage times charge. So in the special case of an electrical current, we can say that E is equal to V times Q, and we still have to divide by T. Now, there's one more formula which might come in useful here, and that, well, you might notice, is that what we have here is V times Q divided by T. Now you might remember that we could write that as V multiplied by Q over T. That's just the same. Now, can you remember what Q over T is? Q is the quantity of charge divided by T, the time. So that is the rate of flow of electric charge. And the rate of flow of electric charge is just current. Okay? I'm going to put this over here. Current I is equal to Q over T. So what we have here is voltage times current. So in the special case of an electric current, we can work out the power by multiplying the voltage times the current. Now, so the formula for electric power is P equals V times I, and this formula is known, at least to CEA, as Joule's law. Okay, now if all of that is a bit much, don't panic. The takeaway out of that is just this. We need to know that power is equal to energy divided by time, and therefore energy is equal to power times time. We also need to know that electrical power is voltage times current. And that's really all. Okay, 32 minutes. If you flip over the page, we have an example to make it real. Okay, let's read the example. A kettle has a voltage of 240 volts applied across its element when it's switched on. It then draws a current of 6.25 amps from the mains supply. So, can we, part A, calculate the electrical power of the kettle, B, say what does that mean, and C, if the kettle takes 3 minutes to boil, how much energy is transferred? Okay, well, let's take the first bit first. We want to calculate the electrical power of the kettle. So, we do this as follows. Well, electrical power, P, is equal to V times I. Now, I'm going to put the knowns and the unknowns here. So the power is question mark. That's what we want to know. V is the voltage of the supply, which was 240 volts. And the current is 6.25 amps. So I for current is 6.25 amps. Okay, so then we can calculate P as V times I. 240 volts multiplied by a current of 6.25 amps. Now, you might have to resort to your calculator to do that. So 240 times 6.25 is 1500. So that's 1500. And we did not mention that the unit of power, well, power is the rate of transfer of energy. So it's the amount of energy per unit time. Energy is measured in joules and time is measured in seconds. So a power of 1500 volt amps is actually 1500 joules per second. And you might remember that the unit of joules per second is given a special name, which is the watt. So 1500 joules is 1500 watts. And the lazy physics notation for that is just big W. So the power is 1500 watts. We could even go one step further and be even lazier. 1500 is 1500. 1500 is 1.5 kilowatts, because kilo stands for 1,000. And that's that. Okay, so remember, what we need to recall to solve that problem was that electrical power P is V times I. And that kind of makes sense because V, the voltage, is the energy supplied per unit charge, and I is the rate of flow of charge. It's the number of coulombs per second. So if we multiply the number of joules per coulomb by the number of coulombs per second, we're going to get the number of joules per second. And that's just the power. Okay. Now, if we go back to our success criteria, we defined voltage. We recalled the general formula for power, energy divided by time, and we've derived and now used the formula for electrical power, P equals V times I. So, now it's your turn, a little bit of formula practice. So, I've been to the library of Spence Towers and had a little look, and I came up with this. This is for GCSE Science, for additional physics, and it's formula practice. I didn't know I had this. So I looked it up, and this is produced, by the way, by the CGP publishing house, which is an excellent source of cheap and information-filled books. Look at all these formulas that they give you at the front. Beautiful. Now, what I've found here is a page of formulas, formula practice for the electrical power formula, V times I. Okay. And a follow-up page with problems to solve, exam-style problems. So what I've done is I've scanned this. I'm going to put this up as a PDF on Fronter, along with the link to this video. And what you're going to do is do them. So I'd say that working through these two pages should keep you inside, out of the sun, for a little while at least. I would suggest do your answers and your working out on a page in the usual way. Don't forget the working out. I'm going to do them too, and then I will put up the answers as well. You don't need to send these to me because it's not going to be an assessable exercise. There's too much there to assess. But you work your way through them, I'll put up the answers, and then you can check to see that it's all working out. Don't worry, there will be an assessment before we get to the end. Look at that, there's more where that came from. Right. Okay, that's the end of the lesson. Off you go and do the exercise, and good luck to you all. I hope you enjoyed learning with me today. I've enjoyed learning with you.